Okay, to set up our lesson for today, everyone, what I'd like you to do is to pull out your book. We're going to do 484 and 485 together. So go ahead and pull those out if you would. And both of these are kind of just an investigation again, a further investigation into these rational or fractional exponents, okay? So let's take a look. If we have these three expressions they want you to compare. Well, I guess we'll do them kind of the way that's set up in your book here. Let's rewrite -8 to the 1/3 and -8 to the 1/4 in radical form. Okay, we'll do -8 to the 2/6 last. So in radical form, -8 to the 1/3 means the cube root of -8. Okay. -8 to the 1/4 means the fourth root of -8. All right. Now, the cube root of -8, don't forget, this is just kind of a little exercise in remembering what it means to be a cube root. A cube root of a number is the number that when multiplied by itself, not twice, but 3 times, will give us -8. Well, that number actually exists. It is -2. It's not +2 because 2 times 2 times 2 would be +8, but -2 times -2 times -2 would equal -8. So interestingly here, the cube root of a negative number does in fact exist. One of the things that we talked about is like one of the major laws we can't violate, like the square root of -9. And I just picked -9 here just because that's a convenient number, right? The square root of -9, a lot of people who, if they're not thinking, they'll say, oh, it's just -3. But that's not true because -3 times -3 equals +9, not -9, okay? It turns out, why did I write this twice? Oh, I'm going to do this, -8, okay? So the square root of -9 doesn't exist, okay? And the square root of -8 also does not exist. Now, don't be confused. The square root of +8 absolutely does exist. That's going to be some number. Well, let's see. 2 squared is 4. 3 squared is 9. So this number here does exist, and it's between 2 and 3. I don't know why I have between. It's funny. Okay, so we're going to get to a generalization in a second, but let's see. The fourth root of -8. Once again, look at this here. We have an even root, Well, there is, and I just lost my thought. Oh, and mind you, notice here, this is also an even root, okay? This is an odd root. Well, an even root of a negative number, there is no number where if I multiply it by itself 4 times, because 4 is an even number, that will give me a negative number. So the fourth root of -8 does not exist. So what that means for us, I actually want to give you a different kind of conclusion to this than what the text is telling you here, because this is kind of how you'll work with this idea moving forward. What we say here is that if we have, right, let's just say b, the nth root of b, which as we know equals b to the 1/n, okay? What we say here is this exists for all b values if n is odd, okay? What we're saying is here, b could be a negative number, b could be a positive number, b could equal 0. All of those numbers, a negative, a positive, or 0, will have an odd root. This is an example right here, right? An odd root of a negative number exists. An odd root of a positive number exists, okay? But here's the thing too, okay? This expression, so let's call this like 0.1, okay? For 2, we're going to say point number 2, it doesn't exist if b is less than 0 and n is even. So what this is telling you is if you're looking for an even root of a negative number, this is not going to exist. I kind of think this is a more helpful generalization here. There are times when you're going to kind of talk about in greater detail next year what the book is trying to hint at, which is taking what's called the principal root, making the assumption that B is positive. But the tie-in in this question with your particular example here is incredibly unclear. So I want you just kind of to delete and just ignore the phrase in your text that says it is customary to restrict the base blah blah blah. Okay, all right. -8 to the 2/6. It's the question the book is asking you to say why this is ambiguous. Well, here's why it's ambiguous. Okay, so if I did this, right, if I was given this expression, it is absolutely okay to do this, to say, well, this is the same thing as taking -8 and squaring it, and then taking the 6th root. There's nothing that is absolutely correct. And we know that -8 squared is 64. Now, 64 is a positive number and is raised to the 1 over n. We're looking at an even root of a positive number. And this exists. Is it 2? 2 times 2 is 4, 8, 16, 30. Yeah, it equals positive 2. Right? But what if we did this? What if someone else went and said, oh, -8 to the 2/6? That's the same thing as saying -8 to the 1/6 and then squaring it, which is correct. And here's where we get into a trouble, because a negative number raised to an even root, or excuse me, an even root of a negative number, as we just discussed, this does not exist. So that's why this is ambiguous. And there's even a third reason why it's ambiguous. Third reason is someone could say, well, let's say I want to take -8 to the 2/6 and write it as -8 to the 1/3, which is perfectly legitimate. And if I write it that way, I get -2. So basically, depending on how you choose to simplify or kind of tease apart that fractional exponent, you get completely different answers. -2, 2, or doesn't exist. That's why that is ambiguous. Okay? 485. X to the 2.5 and x to the 0.3. What I'd like you to do here is just to rewrite x to the 2.5 and x to the 0.3. Please rewrite these exponents that are as decimals. Please write them as rational exponents or fractional exponents. Go ahead and do that and then replay me. Okay? I'm guessing a number of you went and said, well, 2.5 is the same thing as x to the 5/2, and x to the 0.3 is the same thing as x to the 3/10. Okay? Now your text asks you to go one step further. It says, explain why calculating blah, blah, blah is a square root problem. Okay, what I'd like you to do is to rewrite, let's see, I went from a decimal exponent to a fractional or rational exponent. What I'd like you to do then, third step, is rewrite these expressions as what's called a radical expression, okay? So a radical expression is an expression that involves exactly a radical. For example, let's go back up here, okay? These two expressions, -8 to the 1/4 and the 4th root of -8, are equivalent. This expression involves a rational exponent. This expression, it just involves the radical symbol. So let's take a look. Well, this is nothing other than the square root of something. What are we taking the square root of? Exactly, x to the 5th. This expression is the 10th root of something. What are we taking the 10th root of? Indeed, x cubed. Okay, all right. Now we're going to get to, so that was just kind of a little bit of a playing with rational exponents, okay? All right, here's what we're going to do. Major, wow, talk about a major milestone here. Introducing something called the common logarithm, okay? The common logarithm. The first thing I'm going to do is just introduce you to some just notation, right? When we learn something new, we kind of walk through the clumsy part of the beginning, where we just kind of get the language right, okay? So let's start with a couple things. Let's start with writing 10 squared equals 100. Let's see, how about doing this? Oh, I know. 10 to the negative first equals 1/10. All right, let's just start with those. Okay. These two statements, I can absolutely trust that none of you would argue with their veracity or with their truth. These are exponential statements, exponential equations. I could use the word equation because they are, in fact, an equation. There's an equal sign. These are not equations that have an unknown, like an x to solve for, but no one ever said that an equation has to always involve an x variable. An equation absolutely must have an equal sign, and these are equations. I mean, they're just statements of fact, right? Okay, I am going to rewrite these exponential equations as equivalent statements, but rather than expressing them as an exponential equation, I'm going to express them as a logarithmic equation. What in the world is a logarithmic equation? Well, here we go. 10 squared equals 100 is the same thing as, it's saying the exact same statement of truth as this. Log base 10 of 100 equals 2. So important is this new perspective that I want to actually write down the way you say this. Log base 10 of 100 equals 2. This is the mathematically correct way to say this, okay? The kind of layman's user-friendly way to basically make sense of what this is saying is to think of it this way. The exponent that 10 is raised to in order to arrive at 100 equals 2. Okay? So what's so important is this phrase, log base 10, is much shorter than the exponent that 10 is raised to. All right? So log base 10. It's no coincidence that when you say log base 10, look at the exponential equation. Log base 10, right? That which is raised to the exponent is this base right down here. Okay? Similarly, let's rewrite this expression here as a logarithm. Okay? Log base 10 of 1/10 equals -1. So one of the things that people often ask me is, why do we need to write this in different ways? And my answer right now is a partial one. Here's the partial answer. When you write an equation exponentially, look at these. When I write an equation exponentially, the spotlight, the solo spotlight, the person who takes the stage is the quote-unquote result of something being raised to a power. Like, look, he is standing alone, or she, or it. We don't know what gender this person is, what gender this number is, okay? They get the spotlight. In a logarithmic equation, who gets the spotlight? The exponent. The exponent gets the spotlight. Okay. Now you may wonder why, when will we need this? Who cares? You have to hold on that. We're just learning a brand new language. Okay. Log base 10 of 100 equals 2. That means the same thing as the exponent that 10 is raised to in order to arrive at 100 equals 2. Now, you're probably wondering, well, Ms. Yam, what about 3 squared equals 9, or 4 squared equals 16, or 2 cubed equals 8? What about other bases besides 10? Will we ever look at other bases besides 10? The answer is, of course we will. But we will start with the most common, the most convenient base. And the most convenient, most common base is 10. It's so common that 10 logarithms, okay, of base 10 are literally called common logarithms, okay? They're the most common in applications, everyone. They're the most common when we're talking about growth. There's something called logarithmic bounded growth you'll study next year. Common logarithms, base 10 growth is the most common. Logarithms of base 10 are called common logarithms. And they're so common that what's conventionally accepted, do you see this right here? Log base 10 of 100 equals 2. It's so common that when we have a base of 10, we are allowed to not write it. So whenever there is an unwritten, right, there's no base there, it's understood the base is 10. Similarly, when I had this, log base 10 of 1/10 equals -1, this is equivalent to this. So in the future, as we move on, when you just see, and the way you say this, everyone, is you just say log of 1/10. You say log of 100, okay? Now, you can still say log base 10 of 100, but when you don't have the base 10 and you just say log 100, the understanding is the base is 10. Okay, let's just do a little bit of exercise with this right now, please. Okay, what I'd like you to do is to look at number 491. Okay, number 491, it's asking you to do something in the book. I want to ask you to do something additional. 491 says, write each of the following numbers as a power of 10. Okay, here's what I want you to do. I want you to write each of those numbers, A, B, C, D, E, F, as 10 to the some power equals something. So in other words, for part A, the first thing I want you to do is, with that number 1,000, I want you to tell me what 1,000 is in terms of 10. Well, 1,000 is 10 cubed, okay? And then what I want you to do is write each exponential equation logarithmically. This is the same thing as log base 10 of 1,000 equals 3. Look here, I did not write the base 10. You certainly can, but right now we're just talking about common logs, and we know that for common logs, you don't need to have the little 10 there, okay? Go ahead with B, C, D, E, and F, and then replay me, please. All right, so it starts off nice and easy enough, right? B, I think, is fairly simple. I think B is fairly clear. C is fairly clear as well. Let's see, root 10. We have to remember that's the same thing as 10 raised to the 1/2, right? The instructions here were to take each of these numbers, like the number root 10 and 100 over root 10, and this guy was tricky, number F, and write it as a power of 10. So root 10 is 10 to the 1/2, and then here is my logarithmic equation right there, okay? Log base 10 of root 10 equals 1/2. The exponent that 10 is raised to give me radical 10 is 1/2. You want to say hi?
Hi.
Hi. Okay. Now 100 root 10 is 10 to the 2.5. How did I figure that out? Well, 100 is 10 squared, and I'm multiplying. There's a multiplication, unwritten but understood. Root 10 is 10 to the 1/2. Look at this. Properties of exponents. Add the exponents. 2 plus 1/2 is 2.5 or 5/2. And then I've got my logarithmic equation there. And then this one was so tricky. I love this one. So I kind of, broke it down. I'll break it down live time with you. So what I did down here, this is what we started off with, right? And I wrote this as, well, 1 over the cube root of 100 is 10 squared, right? And then I said, well, that's the same thing as 1 over 10 squared to the 1/3, which is the same thing as cube root, right? And then here I've got a multiplication of exponents here, right? But I want to write this as a power of 10, so 10 to the negative 2/3, and that brings me to my, like, right there. So that was really fun. So that becomes log base, the log base 10 on written but understood of the result is equal to negative 2/3. Once again, remember, when you write something logarithmically, the center of the stage, the solo performer, is always the exponent. That's the person that's flying solo here, okay? All right, everyone, what I'm going to do is put your homework up now. Okay, and then we meet live tomorrow and we'll go over this homework together. All right, great job.